what we have here, so as I intersect the line, so we have here your enthalpy, so it's around 42, each closest to 42, so I will assume it is 42 kilojoule per kilogram dry air. Then we have your humidity, so this is now, so let's put ID on this one. So this is now our point 1. Then our wet bulb, this one, wet bulb 1 is equal to, so we have your humidity, so that will be starting from here, that is 5. So you have 6, 7, and we have here 8, 9, and then we have 10. So it can be approximated it as 82. So we can put it here, 82 grams, 82 grams of moisture per kilogram of dry air, per kilogram of dry air. Okay, then it is heated at the temperature of 41 degrees Celsius. So let's plot the 41 degrees Celsius, since we are, so 30, 41, we have this line traveling. So since we are in constant humidity, okay, this one, so we have now your point 2. So we can draw it, the process is like this. Okay, and we can draw the arrow going here. Okay, so from 1 to 2, so we have here, this is label, let's label 1, this is 21 degrees Celsius, this is 41 degrees Celsius. And also we can plot the enthalpy of this line. So ito yun, so traveling parallel to this line, so this somewhere 61, 62, somewhere here. Okay, so traveling parallel, so we have this line now. So let's list down on properties of that, the amount that will be. So this is 62 kilojoule per kilogram of dry air. So see, this will be 62 kilojoule per kilogram dry air. So that is the enthalpy at this point. Now we have the enthalpy 1 and enthalpy 2, no? So this is now your enthalpy 1, and this is now your enthalpy 2. We have now the properties. Okay, then the humidity. Okay, so we'll be needing also the specific volume. So you will notice here we have also a change in specific volume from 1 and 2, no? So the specific volume at point 2, so this line, so that will be kilogram cubic meter, so that will be 0.9, and this one is 0.92. So this can be as, let's say this is 0.92 92. So this will be now cubic meter per kilogram. This is a specific volume of 0.2, and for this one, the specific volume at this 0.1. So we have here 0.9886. That will be 0.84. So it can be, this is 86, 84. This is 86. The middle will be 85. So it can be 0.845 cubic meter per kilogram. So that is the properties at that point. So let's try to list down the properties for each point. So we have now the following properties at point 1 and point 2. Solving for the heat load. So solving for your heat load, that will be your Q so that will be the Q, no? So your Q equal to the mass flow rate and multiplied by the change in enthalpy from point 1 to point 2. So we have the mass flow rate from our given, so that is equal to, okay, so what we have is a volume flow rate, which is 1.5. so we don't have the mass flow rate, but we can compute our mass flow rate. So that is by means of your mass flow rate by means of your volume flow rate 1, then we have your specific volume at 1, where volume flow rate, so that will be 1.5 cubic meter per second divided by the specific volume, which at point 1 we have 0. This one, so we have 0.845 cubic meter per kilogram. Then we have, so cancel out yung cubic meter, so we have the value of 1.775. so this will be kilogram per second. So we have now, this is 1.775 and we have your enthalpy 2, which is 62 kilojoule per kilogram, minus enthalpy 1, we have 42 kilojoule per kilogram. So cancel yung units. So what we have now, so we have 35.5, that will be kilojoule per second, or this will be in terms of kilowatts. So letter B, solving for the mass flow rate of the mass flow rate of the heating water running in the coil. So we'll be using our Q, it can be yung Q natin can be your heat load, or the load from the heater coil can be equated to the equation of M mass flow rate, so specific heat, constant pressure with the change in temperature from T2 to T1. So where our Cp is the specific heat of water, where the specific heat of water at constant pressure, that will be 4.1887 kilojoule per kilogram. So what we're looking now is for the mass flow rate. So rewriting our equation, so that will be our, to get the mass flow rate, so we have your Q of their heater coil divided by your Cp. Then we have the change in temperature from T1 to T2. So the value of your heater coil is, that is 35.5, so that will be kilojoule per kilogram, okay, divided by kilojoule per second, sorry. So this will be kilojoule per second. Kilojoule per second divided by the Cp, which is 4.187 kilojoule per kilogram degrees Celsius. Then multiply it by the change in temperature. So we have that is 85 degrees Celsius minus. Now one problem is what we have here. So the problem does not state what will be the final temperature of the water running on the coil. So I will add the temperature. So let's assume it is, we have 75 degrees Celsius. So let's assume it's 75 degrees Celsius. So substituting here the 75 degrees Celsius, so the mass flow rate is equal to, so cancel out which is yung common, so kilojoule, okay. So using your calculate, so you get the value of the mass flow rate of 0.847, or let's say this is 0.85. So this will be the kilogram per second. Okay, so it's very to understand is just only just follow the equation. So it's very procedural how to solve the problem, and madali nyo naman masusundan, so everybody can follow this one. So this is very basic, no? Very basics from solving, lahat naman nakatapos na ng thermodynamics, so which is yung doon na rin kayo na exercise masyado sa solving of the problems, but this is also a basic problem, so everybody can understand and interpret this one. So next problem, so calculate the load on a cooler coil which cools the moist air in a problem 1. So the last problem, that is heating the air, now this time is cooling, so by 5 degrees. So what is the flow rate of the chill water necessary to this cooling if the flow and return temperatures of 10 degrees Celsius and 15 degrees are satisfactory? So drawing out a schematic diagram, so we have our water in, so stating that the flow of the temperature is from 10 degrees to 15 degrees. So that is 15 degrees absorbing heat, so increase by 5%, 5 degrees, no? Then we have your value, so given that your dry bulb temperature at 1, so that will be, we have 21 degrees Celsius here at this point. Then we have your wet bulb temperature at 1 is also 15 degrees Celsius, and your dry bulb 2, so that will be 5 cools moist air in 5 degrees, so that will be 21 minus 5, so we have 16 degrees Celsius. So here we have 21 degrees Celsius and cools it into 16 degrees Celsius going out here. Okay, then we have the given value of the specific volume we already taken, that will be from the psychrometric chart, that will be 1.5 cubic meter per second. So this time, drawing it in the psychrometric chart, so this time it is opposite. So the flow of this problem, so if we're going to draw the path in the psychrometric chart, so from here we have, so 15 degrees Celsius trival, so we try to plot the line here. So we have 16 degrees Celsius. So here at constant humidity, no? So we have 15 degrees Celsius. So drawing the line. Then let's draw the path from here to here. Okay. Then let's put the arrow for this one. So since this is the flow now, so this will become your 2.2. Okay, for the problem number 2, no? Okay. So let's put it 2 prime. Since we're dealing now for cooling, previously we did by heating, now this time we did it by means of cooling. So looking at on the chart, we have the value, no? So writing it here, no? So H2 prime, it will be, how much is this one? So we have the value of this 36. Okay. So it will be 36.9 kilojoule per kilogram of dry air. So that will be the value for this one. So just copy the properties nun kanina. So since they are the same at 0.2. Now at, so we going to put here 2 prime. So to distinguish the solution. So this is 2 prime. So drive up 2 prime. Okay. Okay, so at 0.2 prime, so we have the enthalpy of 36.9 kilojoule per kilogram of dry air. Then humidity 1 and humidity 2 at 2 prime is equal. So since we have the constant humidity. So solving for the cooling load, again we're using this equation. Again, we have your mass flow rate times the enthalpy 1 minus the enthalpy 2, where our mass flow rate is the same also nung kanina. So it can be expressed as the mass flow rate can be expressed as the volume flow rate divided by the specific volume, which is equal to the value kanina, which is 1.775 kilogram per second. Now substituting the values, so we have 1.775 kilogram per second multiplied by the enthalpy 1, which is 42 minus 36.9. This is kilojoule per kilogram of dry air. So cancelling what is common, so we have the value of 9.05 kilowatts. Again, so your heat load, that will be your Q, is solving for the mass flow rate, that will be equal to the mass flow rate the specific heat at constant pressure, then we have the temperature of the water at TA by TB minus the TA. Okay, so computing for the mass flow rate of the water, so this is W na natin. So we have the mass flow rate of the water that will be equal to Q divided by, so it will be divided by the specific heat of water at constant pressure times the TB minus the TA is equal to, so that will be 9.05 kilojoule per second divided by 4.187. This will be kilogram degree Celsius. Then we have the change in temperature from 15 degrees to 10 degrees Celsius. So cancel out common units. So finally we have the mass flow rate is equal to, so we have the value of 0.433. So that will be kilogram per second. So it's very basic lang naman. So everybody can follow. So madali naman, hindi naman siya totally complicated. Okay? So just take a look at here for the quick overview ng process. No? So next problem what we have here is number 3. So we have 1.5 cubic meter per second of moist air at the state of 28 degrees Celsius dry bulb, 21 degrees Celsius wet bulb, and 101.325 kPa atmospheric flows across a Coil coil, and leaves at 12.5 degrees Celsius dry bulb and 0.0083 kilogram per kilogram of dry air. Determine A, the apparatus dew point temperature, the contact factor of the efficiency of the cooling coil, then we have the cooling load. So establishing what are given, so we have the dry bulb temperature 1, which is 28 degrees Celsius. We have the dry bulb 2, which is 12.5 degrees Celsius. Then we have your wet bulb 1, which is 21 degrees Celsius, and we have the humidity 2, which is equal to 0.0083 kilogram per kilogram dry air. So drawing here the schematic diagram of the process. Okay, you have your the cooling coil here. You have your water in and you have your water out, air entering and air leaving. So let's try to plot these properties which is your given in the psychrometric chart. So we have a dry bulb temperature of 28 degrees Celsius. So from here we have 25, 6, 27, 28. So we have the line 25, 26, 27, 25, 26, 27, 28, 29, 5, 26, 27, so 28. Then we have this dry bulb is intercepted by the wet bulb of 21. So going up, so this is 15, 3, So let's go up. So this is 15. So we have 21. So we have here 25. So this is 20. 20, 21, 2, 23, 24, 25. So this is 21, 20, 21. So this one. Okay. So 20, this is your 21 at this point. Okay. 20, 21. Okay, so this is now your point 1. Where our dry bulb 2 is in 12.5 degrees Celsius. So that is 12.5, so that will be 10, 11, 12. So it is in between. So 10, 11, and 12 here, passing here. Then it is being intercepted by the line of the humidity of 0.0083, so that will be in grams, that will be 8.3. So that will be 5, 6, 7, 8. So we have here 5, 6, 7, 8.3 here. So this one. So we have the point 2 at this point. Now connecting that one. So we have the process here. Okay. So putting the arrow process. So we have now the process 1 to 2, which is what type of process? So we can state that the process is the type of process is. So we have the process of cooling. So you will notice from 28 going to 12.5 degrees Celsius. So it's a form of cooling. Then you will notice the humidity from this is around already of the we get the humidity of is around 10, 11, 12, 13. So it's around 12.9 humidity, then reducing it to 2, so we have the process of dehumidifying, cooling and dehumidifying. So we have the process of cooling and dehumidifying. So question at A, so we're looking now the apparatus dew point temperature, where the dew point defined as, so the dew point temperature is the temperature at which the condensation of water vapor in a space begins. So it is the saturation temperature corresponding to the vapor partial pressure. We're drawing a straight line starting from point 2 as we reach the saturation curve. So this is now your saturation curve. Okay, this one. So this is now our saturation curve. So we determine what will be the temperature from here. So drawing that line going down. So that will be the dew point temperature. So it's here. It's around 9. So it is around 9 degrees Celsius dry bulb. So that is the dew point temperature. So this is also the temperature at which the if you're going to expose the apparatus or the surrounding duct of the system below 9 degrees Celsius. For example, if we have your if we have your FCU here, okay, so the dew point temperature is 9 degrees. If the surrounding temperature of the cooler coil is below 9 degrees Celsius, let's say that is 5 degrees Celsius, then the dew point apparatus outside surface will start to condense. So there will be droplets of water happening around this one. So for the contact factor, we have your equation that will be T1 minus T2, then dew point temperature minus T1, it will be T1 minus the dew point temperature. So where your T1, that will be 28 degrees Celsius. So check that one again, 28 degrees Celsius. So minus your T2, that will be 12.5 degrees Celsius divided by 28 degrees Celsius minus the dew point temperature, which is 9 degrees Celsius. Then we have the value of your CF is equal to, so we have 0.82%, 82. So the cooling coil efficiency, so we have, so cooling coil efficiency, so that will be 0.82 times 100. Then we have 82% efficient yung cooling coil natin, cooling coil efficiency, sorry. So that this determines how efficient our cooling coil, which is this one, how if the cooling coil here serve as well. So the cooling factor, the contact factor determines the efficiency of the cooling coil. So by the change in temperatures,